Hello, welcome back. In this lecture, I would like to continue my description of the quantum phase estimation computing primitive. And in particular, I would like to give you a high-level description of the quantum circuit and say a few words about precision and complexity of the quantum phase estimation quantum computing primitive. So let's go back to the previous lecture. I want to summarize what the phase estimation is about. Well, suppose that we have some QPE operation U that acts on n qubits and has some set of eigenstates that will refer as U1, U2 to Uj. Using a phase estimation, we want to learn the eigenphases associated with each of these eigenstates here, U1, U2, Uj. So the output of the phase estimation is nothing else that eigenphases associated with the input eigenstates. The eigenphase associated with the J eigenstate is always a global phase, right? So it's not a change of the relative phase. Instead, is how the phase of the quantum states are changed. So we can specify it by the angle theta J through which the global phase rotates the register state of each quantum state. This is a high-level description of the phase estimation circuit. You see we have an input as an eigenstate, output that is eigenphase, and then we have the input is the quantum gate we want to know the eigenphase. But let's look in particular each part of this high-level description of the quantum circuit. So the first thing is the input that we have here in this part of the diagram. So Q in is n qubits, so we're going to use n qubits to describe the eigenstate Uj for which we want to obtain the eigenphase. So we know the eigenstate of the quantum gate. We want to know the eigenphase, and we put as an input in our Q in quantum register for the phase estimation. So this is the input, and then we have the main output is Q out. So we initialize this Q out as old 0. So we have here old 0, and then the primitive will use this register to return a binary representation of the desired angle theta J, corresponding to the eigenstate we input in Q in. So we input this eigenstate, and then we get as output theta, that is the eigenphase that is encoded as a binary. So we'll have 0, 1 after the reading operation. In general, the larger we have m, that is the number of qubits for our output, the greater the precision will be. So we will obtain a larger precision for representing theta J if we use more qubits. And then we introduce as an input the quantum computing gate. We want to know the eigenphase. To do that, we actually introduce a special formulation of the quantum gate, and that is a control version of the quantum gate we want to know the eigenphase. So an implementation of the control version of the QPE operation U that we are determining the eigenphase of is the input of this quantum circuit for the phase estimation. So this gate should be passed as a function of the form controlled U that has input and output, which takes a single qubit that will control whether U is applied to the n qubit register out or not. So we know that any control version applies the operation only if the control qubit is equal to 1. In these slides, I present a simple example of how the phase estimation quantum circuit works. So we have our input, that is our quantum eigenstate of the Hadamard gate. So this is the input. We initialize the output, that is the Q out to 0. So all the m qubits are in 0. So this is the 0 state. And then we applied a control version of the Adamar gate, right? So this we can call the CHAD, because it's a control version of the Adamar gate. And as the output obtain the same eigenstate, because by definition, if it is eigenstate, this should not any effect on the eigenstate. And see, we have it here. And then we have the results encoded in binary of the eigenphase in the Q-out quantum register. And then we do an operation here, a read operation here, and we obtain the eigenphase encoded as a binary number. This is 0, 0, 1, the corresponding to quantum state. And this is going to be the main output of our phase estimation quantum circuit. So we obtain this 8 or quantum state 8 by doing this reading operation. But how we can interpret this 8? Well, we obtain our eigenphase by applying the read operation to the m qubits of the output register. The phase estimation quantum computing primitive ends up expressing theta j as a fraction of 360 degree, which is encoded in the output register as a fraction of its size. In this particular case, we know that this particular eigenstate we expect to have an eigenphase of 180 because the global phase is flipped by 180 degree. So in our 4-qubit output register with 2 to the 4, because we have 4 qubits, we have 16 values, we expect the values of 8, since this is exactly half of the register size. Right? So we know that the maximum value that is represented by our 4 qubits will be 15, and we get 8 that is halved, so there's 360 divided by 2 is 180. So this is an important formula that we need to remember to decode the eigenphase from the binary. So we have theta j, and that is the number of our quantum state when we divide it by 360 and multiply by 2 to the m, where m is the number of qubits in the output quantum register. So that also means that whenever we choose m, we also choose a precision for our eigenphase, to express our eigenphase. So the precision with which we can determine an eigenphase will depend on the output register size, that is the m qubits register. So this is the size. If we have 3 qubits, then we can represent 8 states, and then we have here representation in binary, and then representation of a different fraction and the corresponding angle for the eigenphase. So in this case here, for instance, if we use 3 qubits, we see that, for instance, the 150 is not actually represented, right? So we will get a value here. So if you use the 3 qubit output register, the precision won't be enough. The precision in our case, we want to have 150, that is not really represented, so the register resolution will be insufficient. So what happens when we have insufficient resolution? Well, in cases where an output register has insufficient resolution, we found that it ends up in a superposition, a center around the closest possible value. So this case will be around here. You see that circular notation I will look like in the case of our 3-qubit system. So because of this superposition, we return the best lower resolution estimates of our phase only with the sum probability. Obviously, we want to know what would be the size of a quantum register to achieve a certain precision. So if we want to determine the eigenphase to p bits of accuracy and the probability of error of no more than epsilon, then we can calculate the size of the output register that should be employed, m, as this expression here. So we have m, the p that stands for the bits of accuracy, and then we have this operation here that is the so-called ceiling, that is rounding to the next integer. And then we have log as an argument, it takes 2 plus 1 over epsilon. That is our precision. I want to say also about what is the complexity of the phase estimation quantum computing primitives. It turns out that is big O of m square, where m is the number of output quantum register. So the complexity of the phase estimation in terms of the number of operations that are needed to perform depends on the number of qubits m of the output quantum register. And this complexity is big O of m squared. Obviously, the more precision we require, the more QPE operations are needed. And we will see in the next lecture that this dependence of big O of m squared largely depends on the fact that the phase estimation use the inverse of QFT quantum primitives. That is also similar complexity. So because the phase estimation relies on inverse QFT, also the complexity will be reflected in this big O m square complexity. But we're going to look into more in detail the quantum computing phase estimation in the next lecture. This is the last slides, and talk to you soon.